22 7b97z84a elastic OH atoms molecule collisions ultra-cold temps 5G Wow Seti. Actually, yeah. So there's the alien radio signal, September 19, 2013. Previous video was line 22 7b97z83 OH atoms molecules dipolar collisions electric field trap 5G Wow Seti. This is about experimental techniques for cooling cold OH molecules to ultra-cold temperatures. So you can Google the atomic pulse equations. Quotes and PDF file results are found on a blog. Optical dipole force on ladder-like three-level atomic systems driven by chirped fused cycle pulse laser fields. The name of our scientists from June 2012. The link was arxiv.org. So optical dipole force brought this up. Here's a diagram of OH evaporation from a permanent magnetic trap. Looks like the cone that you see on the Minkowski space thing. That's what it looks like to me. In the meantime, our group has also begun exploring innovative experimental techniques for cooling cold OH molecules. Actually, I'm going to put that in there. You never know. That could mean something, right? So we see my thoughts. Diagram above with cone looks like minkowski space, and then it's got an outward flow of energy from the Higgs field hitting and colliding with liquid argon gas and mineral oil covered neutrinos mixing with other particles like fermions, split fermions plus baryons and bosons. Boson C formulas in line 22 and cross-reference particle names lines 1 to 27. Okay, so we're going to add that in there. Okay, so OH evaporation from a permanent magnetic trap. In the meantime, our group has also begun exploring innovative experimental techniques for cooling cold OH molecules to ultra-cold temperatures. Actually, since we did that, I'm going to add the word formula to this because there is a bit of a formula there to try. And I'm going to just make a note that this is a formula now. Okay. Sorry about that. Okay. And just make a space there. Okay, so in the meantime, our group has also begun exploring innovative experimental techniques for cooling cold OH molecules to ultra-cold temperatures of less than 1 mK. Until recently, many physicists considered it difficult, if not impossible, to evaporatively cool molecules. Because their collision behavior is far more complex than that of atoms, the conventional wisdom was that it was unlikely that cold molecules would collide and bounce off one another often enough to facilitate the kind of stepwise cooling that works so well with atoms. In atomic collide and bounce collisions, known as elastic collisions, let's add some elastic collisions up here with other, and then we're going to add elastic collisions. And add some atoms, and we'll add some proton energies to this mixture. Okay. Known as elastic collisions, some atoms are left much hotter than the others. So the hot ones can really agitate the molecules in the cold ones, because heat speeds up molecules when you add. There we go. Okay, so we got some hot atoms. We're going to add microwave laser beam energies, and this will collide the warm atoms that are circling around the protons, electrons, and ultra cold rubidium atoms, and then we have the C60 laser. I don't know how that comes into play. And then we want to add the KRB molecules to this mixture. Okay. So, okay, the conventional wisdom that is unlikely that the cold molecules would collide and bounce off. Blah blah blah. Let's go back down here. Some atoms are left much hotter than the others. By removing the hotter atoms, researchers are able to get the remaining atom gas to cool rapidly to ultra low temperatures. So you could separate the two and then stick them back together. So you'd have them going through some sort of laser device, which would be the turbine. Okay, so when you want to separate the atoms, separate the atoms with the turbine invention found in Wow data. I think it's between lines line 22 or line 20, not sure. We'll have to cross-reference it to find it. To find turbine. It's a turbine invention with the laser beams, and then we add the atoms, cold atoms, and then we have another laser beam, which would be the warm atoms. And we have two different types. We got electron ribbon lasers, and then we're going to have pencil beam lasers. And I would think with our pencil beam lasers, let's make those the ultra cold rubidium atoms if we can. I'm not sure if this will work. It's just an idea. Okay. Yeah. So we're going to remove the hotter atoms. Researchers are able to get the remaining atom gas to cool rapidly to ultra low temperatures. So our cooled, ultra cold rubidium atoms, and we're going to mix those with the liquid cool plasma and liquid argon gas, okay? And that'll give us a nice cold temperature to work with. Okay. So in 2012, our group, along with theoretical collaboration from Gulvin, Kumar, and John Bone, succeeded with an innovative evaporative cooling experiment with a molecular gas of OH. Even though the initial demonstration cooled the OH molecule shown, so we want to do we want to look at the 2012 theory of these two. Okay, we're going to add it to this add other theory. I'm going to have to Google it in another video. Okay, so we're going to have to Google it in another video to find out what that is. So I'm going to do that over here. Actually, I'll do it in the next one, and I'm going to have to change my numbering. That's all. So this will be 84A. So I'll make it 84C, okay? That way I don't mess up too much of the numbering. That'll be 84C. Okay. From formula in 84A. There. Okay. I'm really muffing this up, aren't I? Sorry. Okay, so yeah. Quote from blog. Go back to quote from blog. Okay, so we're back down here. So even though the initial demonstration cooled the OH molecules down to only 4 MK, it was so successful that the group is optimistic about being able to eventually cool an OH gas to reach quantum degeneracy. We covered quantum degeneracy in the future. There's formulas for it too. This will be an exciting step to open the door to studying the ultra-cold chemistry of familiar molecules that exist in the natural world. And that's from the website gila.colorado.edu. The keyword in the next video it'll be OH evaporation from a permanent trap. No. It's going to be precision RF knife for OH evaporation is what we're going to look at in the next video here. Okay? Thanks for watching. Drop my camera.